We're live!
Woo!
The
Hello.
internet. The internet. Hi, internet. So, let's do our traditional introductions, except this week I'll make you go first.
Oh, okay. Well, I'm Dan Dorman. I am a developer at Instructure. Mostly that means Ruby and Ember JavaScript stuff right now, which is fun. Yeah, and I like doing computery things on the side too, so that's why I'm here tonight.
Do you like working on both the back end and front end, or do you ever wish you could work more just on one or the other?
No, I really like doing both. I think I like having an excuse to work on all manner of things. So it really kind of depends, like what my current focus is. I think there's a lot of interesting things going on in the UI right now. I think web programming in particular is a lot of fun. There's a lot of interesting things to work on there. But I really like writing server-side and Ruby code too. So I think that's awesome. I'm always looking for opportunities to mess around with new languages and things too. So I hate to pigeonhole myself as like a Rubyist or a JavaScript guy. I kind of like to think of myself more as a programmer because whatever strikes my fancy. I'm probably thinking of looking at like the Project 6 where you have to write your own little compiler. I'll probably do enclosure just because I want to have an excuse to write more enclosure. So if I don't just take the plunge and do it, it's not going to happen. So anyway.
All right. Well, I'm Michael Reese. I'm a developer here at Monday Desktop. I'm actually happen to be in my office tonight because tonight was URUG, our monthly Ruby users group, and that is held here. So I just happened to be here extremely late in the evening, like an idiot, instead of at home. And so hopefully I'll be there before too long. But yeah. So I actually, in these days, I am almost entirely a Ruby guy at work. And so I've been finding myself spending more of my free time branching out into other things for fun. I used to be at my previous job, I was more of a full stack developer, and I enjoyed that. But there was also times where I wished I had more time to devote to just trying to create clean code on the back end. It was an area that I was interested in. And so I've been getting to do a little bit more of that, but also just after a few months of doing that, I'm just starting to get the fever for more cowbell or JavaScript.
Yeah, it's hard. It's hard to avoid it these days, though. You should maybe enjoy it while it lasts. I have this like apocalyptic vision of the future where all we'll ever write is JavaScript. That's all I'll be able to find paying jobs doing. Like I don't have a problem with JavaScript. It's got its foibles and warts as a language, but it's also there's a lot of fun things you can do with JavaScript as well. So I'm definitely not a hater, but man, I just hate getting stuck writing the same kind of stuff all the time. When there's so many exciting paradigms and things to explore out there in the world of computer science.
Yeah, that is interesting that you have that apocalyptic vision of the future. I am not a hater of writing JavaScript in the browser, but sadly, even though it's very unfounded, I think I actually am a hater of writing JavaScript on the server. And there's no good reason for it other than all my experiences of trying to do it have been terrible. So it's probably my own fault.
I'm actually totally with you because I'm like, well, you have to write JavaScript in the browser, so you've got a choice on the server. Why would you pick JavaScript? Is kind of my my argument. But there's really no logic behind that either. I mean, if you like JavaScript, it's cool, and there's some benefits to that model, I guess. But yeah, I think that's your chance to spread your wings, programmers. Don't squander it on JavaScript.
Don't waste your life like I've wasted mine.
That's right.
All right, so I guess we should probably eventually cover Nand2Tetris material. It's probably a good time now.
Right.
So we're going to be going over week 5, project 5, which is it's back writing some more HDL. Last week we had a little break of writing some assembly so that we can learn what we need to implement and the final steps of our hardware. And this week we're back in HDL. And first question I have is just kind of what was what was your experience overall with this week's project? Was there anything that stood out as harder than the rest or more confusing, anything like that?
Nothing struck me as particularly hard or confusing. Definitely the thing that sticks with me, though, is that the CPU was like easily the heart of the thing, and everything else was pretty much a walk in the park. Even like the computer was just pretty much just wiring up the trickier parts. The CPU was the fun part.
Yeah, I had that same experience, and it was to such a degree that it even made me think. I don't have a good proposal for this, but it made me think: is the CPU the God object of the computer? Because it seems like it just was the one place where they're like, oh no, we don't want keyboards to be like a thing, so we'll just make them memory addresses, and we don't want the screen to be a thing, so we'll just make it memory addresses. But the CPU is where all the logic for all the things exists, and it made me wonder. I know that that's how we do it. I'm sure lots of smart people have spent time thinking about this, but at least I was like, I wonder if it'd be possible to break down that CPU or break apart its responsibilities a little bit more. I don't know, just an idea.
Interesting. Object-oriented CPU. I did not think about that at all. That's interesting. One of the things I did think was interesting, though, was the programs themselves are not like software in the sense like, oh, you load up a program and you run it dynamically. It's like this. Like even their concept here is like, no, it's this hard-coded ROM program that's all that computer, like once that chip is there, that's all this is ever going to do. So, I mean, of course, Word is totally simulating that, so it's all software anyway, but it felt like it was an interesting trade-off.
Did it make you think of Nintendo cartridges? That's what I always think of when I see the ROM part of it. I'm like, oh yeah, this is where you plug in the thing, but you have to blow on it first to make sure it's still working.
That's right, man. Yeah, actually, that did come to mind.
All right, well, should we? I guess we should probably look at some code. So I'll pull up real quick here. The one benefit of being in my office is that I have two screens, so when I share my background, it doesn't turn into an infinite recursion, a visual infinite recursion. So I'm guessing that you had probably a similar experience based on what you said so far, but the putting together the memory was pretty simplistic. I mean, obviously they had planned this out in advance because the way that the addressing works is that like because you address using 15 bits, but your RAM is only 16K, so that you only need the first 14 for the RAM, and then you use that last bit to basically be like the keyboard address, and the screen addresses basically takes up most of that 15th bit of precision, and they happen to pick the addresses just so that they like lined up perfectly with one of those 15 wires. Was that sort of the same thing you had?
Yes, that is. I have an extra chip, and I'm wondering why. I must have done something weird. I was using a DMUX 4-way for some reason. And
pull it up. I want to see.
Yeah, okay, that's a good idea. Come on. There we go. Share this time. All right, so, man, it's been long enough now that I don't remember why I was doing it this way. Why am I ORing this? Nothing makes sense. Like, it's obviously the same basic thing you're doing. I just have this extra DMUX 4-way and an OR for some silly reason. Well, yeah. I wish I could explain it, but I can't.
Oh, let's see. So you have a RAM load 1, a RAM load 2, and a screen load. And I just use a single DMUX, so hang on, I'll switch the view. Back over to mine real quick. So I just have a single DMUX, and then I just have whether or not to load the RAM or the screen. And
it seems like a more straightforward way to do it.
Interesting, because you're using your A and B, which is.
And then I ignored the D anyway. So.
And then you end up ORing together the RAM load 1 and the RAM load 2. So yeah. Anyway, I think it equivalences to the same thing, just with an extra chip in there.
Yeah, well, that means you win. You are a prize winner this week.
Yay! Internet points. And then it looks like the MUX 4-way 16 is the exact same thing.
Yeah, it looks like everything else is pretty much... Yeah.
What's funny is it looks like we are actually converging on a naming convention between the two of us. Because look at our last chip is like virtually identical. Like character for character, almost identical.
I just have a little more white space. That's it. That's it.
Oh, yeah. You are so much better than me at white space. That actually happens every single week when we talk. I'm always like, oh, yeah, I should put spaces between commas.
I don't know why I don't put spaces in between the like equal sign. I usually do that in my Ruby code, but oh well. You know.
Oh, well, there you go.
Different beasts. All right.
So the computer, I don't even know if this is worth talking about. This was like definitely by far the easiest. Is there a consensus on that?
It looks like the same 3 chips.
Yeah, I think we move on to the CPU. It's like literally it's just the wires between the components is all the computer really is.
Yeah, it was pretty easy time. I was glad it was last though. You know, it's a nice easy way to go out.
It was. All right, so CPU. This is definitely, like we talked about, the trickiest of the things we had to implement this week.
Yeah.
So I'll just run through kind of the ideas that I put together in here, and then I'll just would like to see you walk through yours to get an idea of what's different. The first thing so this is actually a gripe. This is my first gripe about the content of this course so far, is that in the chapter where they go over the machine language, sorry, I'll start sharing my screen for just a second so I can gripe face to face. I'll face my accusers. So my rant is basically in the machine language definition, they name the different parts of the instruction, like J1, J2, and J3, right? Those are the 3 bits that determine the jump.
Yes.
But because they're using whatever endianness they're using when you're in the HDL, the numbers are like backwards. So
that was terrible.
So I'll pull it, for instance. So like I have all these comments to myself up here to be like, oh, J1 is actually instruction bit 2, J2 is instruction bit 1, and J3 is instruction bit 0. And like all of the bugs that I ran into implementing the CPU were basically about me accidentally reversing these things in my head. And so if they had just named the J1, J2, and J3 like the order that the bits are specified in the HDL language, it would have been a lot easier, I think. And I don't think you learn much by translating those.
Okay.
So anyway, I wrote myself a bunch of notes about like what are the different pins. And obviously all of these pins are only those things if you happen to be running a C instruction. If you're running an A instruction, basically all 15 of your pins are just the address value that you want to load into the A register. But really the only thing that I found tricky is wiring up these function pins to the arithmetic logic unit. Because these ones were all just kind of like, oh, this pin just means, do I want to write a value into the D register or not? Do I want to write a value to memory or not? And so they all pretty much just map straight to other pins.
Mm-hmm. Yeah.
And then these were really the ones that were tricky because there wasn't, certainly in like the machine language chapter, I didn't find any sort of like guide. It just had like the truth table of like, oh, if you're running a C instruction and these are your 5 values, then it should compute A plus D. And so it was just a lot of like, I just kept looking at that truth table and being like, okay, all the things that look like they are additive operations seem like they tend to center around C5, so that must map to the function pin or this F pin on the ALU, which determines whether or not you're doing a bitwise AND or you are doing a addition as the operation on your 2 entities. And anyway, and then so I just had to go through a deductive process to figure out that then this pin maps to setting one of your values to 0, and this one maps to doing a bitwise NOT of one of your inputs, et cetera, et cetera. So once I had those figured out, then everything else was mostly easy, because you essentially just use that 15th or that 16th pin, the final pin, to decide whether you're doing an A instruction or a C instruction. And the only reason I even did these NOT gates is really just so I can name that pin something easier to read.
Yeah, yeah.
And then you just have your A register where you're just like, hey, if this is an A instruction, then like set the load pin and write a value in there. That's basically it. D pin, D register is pretty much the same thing. The ALU, like I said, the main thing here was just about you just have to AND together, like if this is a C instruction and this certain pin is set. And again, actually these ANDs I really only care about just because I wanted to give names to these input pins here. So this would all be optimized out for sure by any sort of HDL compiler. But I just wanted to map to these names because when I was playing around with like, oh, I want to swap this value, this pin for that value, I was trying to figure out what the correct ordering was. It was easier to leave this guy specified this way and just change the definitions up here. So,
yeah.
Then you have your jumping logic, which was a little bit tricky, sort of, not too bad. Just a little bit of logic to say like to do like the less than or equal stuff, but that was about it. And then all those things. So I just basically said, here's all my internals, and then here's all my outputs. And my outputs are really just like, am I writing a value to memory? Which, like I said, is just if you're running a C instruction and this pin is set, then that means I want to write to memory, and et cetera, right? So that's basically everything I had. So let's get a tour of Dan Dorman's brain via his HDL.
All right. Well, a lot of that feels like very similar, and I guess that's because, you know, that's how it goes. My screen is up. Okay. All right. So I kind of did the same thing where I just like named all the chips, like with this crazy thing here. And another convenience like you did where it's like, oh, is this an A instruction or is this a C instruction? Whoops. And I kind of called this like adder instruction or comp instruction. Was sort of the mnemonic there. And then I just sort of like named all the pins individually. Like with C, that was like kind of the shorthand for, okay, this is C instruction, and then this is the J bit, and it's J3. So on and so forth with D and C. I don't remember like struggling with the pins for this part. So I don't know if I just like lucked out and like blindly just happened to like have it work the way they were arranged, or if there was something in the reading that I just picked up on, but I don't remember that being particularly tricky once I figured out that the bits were all like reversed. That sucked. Those were like very subtle errors. I'm like, why is this failing exactly?
I just, your AND16, your way of creating all your internal names in one place, that is pure brilliance.
I guess. So I'm not afraid to throw in extra chips for convenience sake. Like you did in some cases. Like, this is only here because I wanted something to refer to like a Boolean adder inst thing later. I could have just dereferenced this somewhere else later, but I didn't want to. So well. Oh well.
It's so funny to hear you say dereference when you're talking about hardware. But it's totally the way you think about it. It's all the same concepts, right? It just happens to be happening with electrons instead of bits.
Yeah, fair point. And so some of the stuff that I noticed you grouped under like output, like I think I grouped up here by the register, like where I'm writing it, and like saying, okay, am I going to write the A register here, and then just handle that right here, and same thing with the D register. Just check that pin and then see, oh, am I actually doing a computation instruction? Then I need to write this thing.
Yeah, it looks like our two registers are basically identical, except I'm doing my like renaming of pins right by the A register, whereas you had your brilliant rename all the things up front.
I guess some way. And then I do like how you actually had like names for the things so they were like the same, so you'd know. Although, I don't know, I guess maybe there's some utility in saying, oh, this is which pin maps to which output in this thing. I like both for different reasons. Yeah, but other than that, I mean, I don't think there's a whole bunch of difference there, just shoving the pins into the ALU.
Yep.
And the jump, I think I reordered a little differently, but at the same time, based on a rough count of the number of chips involved, I think they're about the same, so I'm sure we're pretty much doing more or less the same thing.
Yep, looks like it.
And then just ending with the program counter update.
Yeah. Did I do a program? Oh yeah, it is in there. Oh yeah, it's in my output section. Yeah.
Yeah.
All right. Well, yeah. I mean, it looks like the two implementations are very similar. I think we'll award this chip to you as the winner because of your rename all the things together, and using that mux up front to also determine your A instruction, C instruction was quite clever.
Oh, thank you. You're too kind.
Anytime.
But I have to admit, like, it was super cool once this all got like working. To like actually see it like running programs, like have this generic processing thing that could just do all these crazy things. It was really cool. Got a real kick out of it.
Yeah, to have like a simulation of a von Neumann machine actually working, like, and know that you built those things. Like the little bits of it they're not real, but they're all the virtual bits of it are things that you made, and it's pretty cool.
Yeah, it was a real rush. It was a ton of fun. I had a lot of fun doing it. I guess one thing that I found interesting, I wonder if you had the same experience, was like how much of this I had to build before I could do anything with it at all. Like my normal inclination, I guess with software especially, is just kind of like build up tiny little pieces of it and sort of grow it incrementally. But here I felt like so much needed to be in place that it was really hard to do that. Like I had to be like thinking about how this would probably flow well before I could start running it. Were you able to do it incrementally, or did you kind of have to do like a lot of upfront stuff before you could start iterating on it?
That's a really good question. I actually, I wonder if some of the pain that I was expressing about trying to figure out the correct mapping of which instruction pins turned into which ALU pins, if that is a similar sort of pain. I wasn't thinking of it in terms of like, oh, it'd be nice to do this incrementally, but certainly in retrospect, I had the same experience where it's like you can't even bother running the test script until you at least think you have it sort of mostly right, because you can't control the order of which tests are going to get run or any of that. So it's like it'd be really cool if there was a way to say like, oh, do all your memory tests first, and just let's make sure that I have like whether or not I'm writing and reading from memory. Let's just make sure that's right, or like just testing the stuff of like loading things into registers, just what gets loaded into registers, and don't do any ALU computations yet. It'd be nice if you had some, like, it's super nice that there's a test at all. That's
true.
That's extremely helpful compared to the alternative. But it does sort of feel like there's just a big integration test, and there's no way for you to unit test the pieces of it together.
Yeah, that's I think what was rough. So I just kind of had to like think, oh, it all worked. So I didn't actually find out about the pins being in the reverse order until everything was put together.
I really hope there's a new revision, and it'll have a foreword accredited to Dan Dorman saying, we have renamed all the pins in the machine instructions section of this book to be the same order as we specify things in HDL.
Yeah. It's real nice to like see like these variable names like decreasing as their corresponding indexes increase. It's like, what were you thinking, guys?
It's the funny thing is it's easy to complain about because honestly the rest of the book is clearly they have like thought things out very carefully when they were organizing this. Like at least from my own experience of being in some college courses that did similar things, but we tried to implement like the original x86 instruction set, which like is way worse. It was way worse than trying to implement this, and it's because they were pretty thoughtful about saying like, oh, let's just make sure that our ALU really only supports this like most basic set of operations, because that way we can fit everything into a 16-bit machine instruction, and the pins do end up actually mapping pretty much one-to-one to the ALU pins. And that's like, I think, not true for most modern CPUs, or even most basic CPUs. They tend to like have less input pins that have more cryptic meanings, and you like much smaller portion of your instruction actually goes towards specifying the operation that you're trying to compute. So anyway, like clearly they have done an amazing job of setting out the content of the course, and this was like the one place where it felt like there was a big gap, where it just was like, we'll do things in this order and then we'll do in reverse order, and figure it out, students. And so anyway, it's easy to complain as a consumer, right?
Yeah. Yeah, but I'd agree. I think, like, all in all, I've been extremely impressed how things have been laid out and presented, and just, like, this building on top of the previous stuff. Even the fact that the previous week was, you know, doing some assembly programming rather than doing the CPU and then going into software. The fact that they had that detour and then came back makes a lot of sense in retrospect.
Yeah, so, and I think they've done a great job of, like, the things that they've chosen to simplify, like simplifying their the ALU so that the CPU can be somewhat simpler and all that. Like, I think every one of those decisions in retrospect, I'm like, I feel like it didn't really take away from my learning. Like, I know that a real CPU is more complex than this and doesn't happen to have all these nice qualities of everything mapping one-to-one or very closely one-to-one, but it's still like, I still understand the basics of how a memory thing works and how a CPU thing works, and I can appreciate it more now. So I think they strike a really good balance of simplifying the things that make sense to simplify, because they don't take away from the learning of it.
Yep, fair point.
Well, do you have any final words of wisdom for anyone who might be trying to implement Chapter 5, Project 5?
No. If you have watched our video, you have learned all the dark secrets, which is mostly watch out for that pin order when you're doing the CPU.
Yeah.
You should be fine.
All right. Well, I think that'll be a wrap then for us for this week. Our video chats have been getting somewhat shorter, but I think they actually are pretty. I've been happy with like the content of them. I feel like it's a good conversation. It's a conversation that, as someone, just if I was reading the book on my own, I would find these discussions very interesting. So thanks for coming online and doing it with me, Dan.
Yeah, well, thanks for hosting, Mike. It's always fun.
All right. Well, I guess we'll see everyone next week. Dan, do you think a week is realistic for Project 6?
It is for me, because I'll be honest, I sort of started on it kind of. So when I said I might do it in Clojure, I mean I've started writing it in Clojure. So yes, I think about a week should be fine.
Oh, okay. I will look forward to seeing your Clojure implementation. I have totally not started it yet, even though I did finish this project. You know, we delayed this episode by a week, and I totally could have gotten started this last week, but I was super engrossed in playing in the world of JavaScript and ClojureScript and React, and just taking a little detour from the normal things to play around in the JavaScript world for a little while.
Okay, React is cool tech. It's just looking at Facebook's on a roll. They put out that Jest testing library today that I want to take a look at next. So.
Well, we might have a follow-up study group doing JavaScript things then, maybe something like that.
All right. Sounds
yeah, so thanks again, Dan, and I think we will plan then on just a week. I'll put up the video page a little bit early, and hopefully we can then comment on it if it looks like it's taking us too long or whatever.
Okay.
I'm not upset at all if we push it back a week, but I think a week is probably reasonable for me too. I'm getting to the point where I have kind of wound down a little bit on my other experimentations, so I think a week will be a good amount of time for me.
Cool. Sounds good. Well, we'll see how it goes then.
All right, sounds good. We'll see you next week, Dan.
All right.